So in this tutorial part now, we are coming to a point where building our understanding of gravitational acceleration, we are trying to attempt more complex mass-based systems, right? We have looked at equilateral triangle system, we have looked at 2-point masses, but there is something called as quadruple, and that's exactly the tutorial question that we are going to attempt. So the question is the following. 4 identical mass m are located at the corner of a square. You want to find out the tangential velocity of each mass m revolving in a circular orbit. So the question therefore states in a diagram a very simple point, right? There are 4 masses of identical mass m which are located at the corner of a square of size m. They are revolving in a circular orbit, which means this orbit is circumscribing this square, standard geometry, or alternatively this square is getting inscribed in this circle. We are expected to find out the tangential velocity of each of the mass, right? Now, such questions need to be attempted more from a basic understanding of Gm/r² formula that we looked at and the quick handle on the geometrical part of it. First of all, before doing anything, I would like to find out all the properties. Let's start numbering these so that till the time we derive the values, we know what we are calling it to. Each mass is getting influenced by other 3 masses, right? It's a double symmetry problem. What does that mean? If I have a mirror symmetry here and a mirror symmetry here, it's a doubly symmetric problem. So no matter one of which mass I look and analyze at, the same analogy holds true for other 3, right? And that's the beauty of this mirror symmetric or doubly symmetric systems. Typically some of these systems are found in astronomy as well, where you will have a quadruple of stars revolving in a almost circular orbit. So this is a very important aspect of it, right? Now, this mass 1 is being exerted a gravitational pull force from mass 2, mass 4 and mass 3. I know the distance between these 2 masses, right? Now let us start writing a body diagram. What is the body force diagram on mass 2? You have a gravitational force of attraction which is Gm/r². Because of this other mass, and I can call this r as A. The same force is also exerted by mass 2. Okay? So these are the 2 forces. At 45 degree, the mass 3 exerts a force which is Gm/r². I just don't know this. And that's where a simple mathematics comes into picture. This is an equilateral triangle, both sides are same. And this is this triangle with this 90 degree angle. So this is 45 each. So this will be root 2 times A. So this has to be 2A². Which means, and because of tangential velocity V, how is this mass having a centripetal force to balance it? If you sit on the mass, it will be centrifugal force, right? And how will that centrifugal force look like? It will be in this direction, mv² upon r, right? What is the radius of this circle again? Root 2 times A. Because what is the diagonal of a triangle? This square is same as the diameter of the circle, right? So we have now all the picture. If I am talking about force, I will have to multiply each with mass because it's a mass multiplication, right? Now, all the thing that you have to look at here now is balancing about which axis. Since these forces are in this axis velocity, perpendicular to the direction of velocity, I will resolve these components also along those axes. So, I have this force component. Now, please take a close attention, right? This force has resolved into this component and this component. Same way, this force is resolved into this component and this component. But resolution of this force in this direction and this direction will cancel each other, right? So there is no force in tangential direction. That's the most important point expected to move in circular orbit, right? So the force in this direction would be gmm upon 2a square plus gmm upon a square cos of 45, which is 1 upon root 2 multiplied by 2, because not only this force but this force both together are giving the same projection in this direction. So I can just multiply it with 2. This force has to be balanced with centrifugal force. So this is my equation. 1m has to, of course, I know, get cancelled throughout. 1a will also get cancelled across. So what I am left with is v square. Now I will start making simplifications. This root 2 comes on the top. Gm, of course, comes out. This root 2 cancel this 2 to leave 1 upon root 2 in the denominator. Right? So 1 upon root 2 is in the denominator, and this root 2 gets multiplied with root 2 to give me 2. So finally the velocity of the mass is gm 1 by root 2 plus 2 whole thing in the square root. And because of the double symmetry problem, the velocity of each mass is identical. That's as simple symmetric objections that we have been looking at. One small tweak which you will always see in any of the objective examination questions, such as GATE questions, would be they will just modify this question by making one of the masses 2 times the m. The components and the resolution still remain the same. Because the problem is still doubly symmetric, the whole thing you have to understand is this 2 does not change anything. The velocities will be different. But if both of these are 2 and both of these are m, the orbit will start becoming elliptical rather than square. And so you would have something like this orbit in which a rectangle will be formed. Such questions also require exactly identical analysis. The tangential velocity offsetted through its force by other 3 masses. So you have to be very, very careful about this force resolution and component matching of the forces irrespective of the mass system. That's all it needs in objective questions.